The last part of this chapter is on stoichiometry. Stoichiometry is the process of using chemical equations to calculate how much you have of something from something else. We're basically combining balancing equations and molar conversions. It looks pretty crazy here. I know that. We're going to practice. It's not terrible. Your overall goal in stoichiometry is going to be you're going to be given something. You're going to have to convert it to moles. Then you're going to have to convert it to moles of something else using your balanced equation. And if necessary, convert back out. The only way we can compare things is in moles. And we make the assumption that the coefficients in a chemical reaction represent the number of moles you have of each substance. These are called mole ratios or mole bridges. I usually refer to them as the balanced equation step. They're conversion factors using a balanced equation. So for example, you would have 1 mole of N2 for every 3 moles of H2. Or you'd have 2 moles of NH3 for every 1 mole of N2. There are quite a few others, but we're just using the coefficients to compare. Knowing what coefficients to use depends on the specific question and what it's asking. The first type of problem we're going to discuss is called a mole-mole problem, and it's because it gives you moles and asks for moles. There's a general equation for this, so it's your given over 1. And then it's our balanced equation step, which is the coefficient of what we want divided by the coefficient, or the moles, of our given. We'll use this on the next slide so you get an idea of what I'm talking about. So let's do this practice problem. The first thing you want to do whenever you do any type of stoichiometry problem is make sure you have a chemical reaction of some sort. If there is a reaction, it's going to be some form of stoichiometry. And then a lot of times you have to balance that reaction. I'll do that for you here. And then use the balanced equation. So the question is asking us to calculate moles of oxygen, and it gives us moles of aluminum oxide. So our given is our 3.34 moles of our Al2O3. And we're going to put that over 1 just like normal. And then I'm going to use my balanced equation to figure out my second step. I want oxygen, and in my equation I have 3 oxygens. So it's 3 mole of O2. And I'm getting rid of my aluminum oxide, and I have 2 moles of that. We're still doing dimensional analysis here because the moles of aluminum oxide are going to cancel. And then you would just multiply and divide to solve the problem. You should end up getting 5.01 moles of O2. You'll notice that nowhere did I do anything with the aluminum that's by itself, and that's because the practice problem didn't say anything about it. It wants us to focus on oxygen and aluminum oxide. And you'll notice that I label this as my balanced equation step because the numbers I used, my 3 and my 2, came directly out of my balanced equation. Please pause the video and attempt the bottom 2 problems. Please check your answers. You should have started with the given for each one over 1, and then compared the 2 substances that they asked you about. It is really important that you label your substances here because these get more complicated. But again, it's still just dimensional analysis. So moles of C5H12, it's on top, and they also go on the bottom. I used a 1 and a 5 because those were the coefficients. In the second example, again, moles of CO2 will cancel, and I'm comparing oxygen and carbon dioxide, so I'm using the 5 and the 8 in my mole ratio. Let's continue on. The next type of stoichiometry we're going to talk about is known as mass-mass, and that's because it's grams of one thing to grams of another. This one looks much more complicated than the other one, but it is doable. You got this. So you're going to take your given over 1. Then it's 1 mole of the given over its molar mass. Then it's our balanced equation step, which will be the coefficient or moles of what you want over the coefficient or moles of the given. And finally, it's going to be the molar mass of what you want over 1 mole of what you want. So here, you're converting from grams to moles, just like we did in the past. Okay, grams of A to moles of A. Then this step is allowing us to convert from moles of A to moles of B. And then here, this is allowing us to go from moles of B to grams of B, which is what we want. You need 2 molar masses. When you're first learning this, sometimes it's helpful to first calculate the molar masses. I do like to do that in advance. So I'm going to find the molar mass of SiCl4. I get about 168. And I'm going to find the molar mass of magnesium, where I get 94. So I'm going to do that in advance. And then I'm going to follow my general equation. So I'm going to start with my given grams of my MgCl2 over 1. I'm going to convert this to moles by using the molar mass. Then I'm going to do my balanced equation step. I want SiCl4, and I'm given MgCl2, and we completely forgot to balance our reaction. My fault. Let's add that in right now. So I'm looking for my SiCl4. I have 1 of them, so it's 1 mole of SiCl4. And I'm getting rid of my Mg. I have 2 moles of MgCl2. And then my final step is to use my molar mass of what I want over 1 mole. Once again, I'm able to cross things out. So grams of MgCl2 go away. Moles of MgCl2 cancel. Moles of SiCl4 cancel. And then I'm able to solve my problem and round for sig figs. So we followed our general equation, okay, which is exactly what you're going to have to do on the next slide. Now, for both of these practice problems, you have the same balanced equation. It is already balanced for you. You would know this is a mass-mass problem because it asks for grams and provides you with grams. So at this time, please pause the video and attempt both of these problems. Please check your answers. Okay, you start with your grams of the given over 1 mole over its molar mass. You'll notice here that I did not write the word mole. You still can. It's just not necessarily required. We're using the equation. And then the molar mass of what we're looking for is aluminum. Now, one of the biggest mistakes I see with this is instead of the 27, someone will put 81. And that's because there are 3 aluminums. When you are finding molar mass of a substance, that's why I like to do it in advance before I even look at my reaction, it's focused on just one of that substance. It doesn't matter what the coefficient is when I'm calculating molar mass. My coefficient portion is right here, and therefore I don't need to triple or quadruple or whatever with the mass. I want the molar mass of a single substance, disregarding its coefficient. The second example I did not write quite as much. As you get better at this, this may work for you. Okay, I wrote the minimum amount of work that would be required to earn full credit for the question. So you'll notice that I didn't label my substances at all except in the balanced equation step. However, I still did all the math. I still have some units labeled to find my final answer. Okay, so this is that second one. That's fine. That's the minimum amount of work that you would have to show to earn full credit for that question. The next part of the chapter discusses limiting reactants. In this course, you just have to learn what they are. It is the reactant that stops production because it runs out first. It gets used up. Okay, and in this burger example here, you have 10 buns, 5 burgers, 4 pieces of cheese. So each burger, of course, requires 2 pieces of bun, okay, or a bun, 1 burger, and a piece of cheese. If you were asked to tell me what the limiting reactant was, the one that stops the reaction because it runs out, hopefully you would tell me cheese, because you have less cheese than everything else. And then what's found in excess would be the extra buns and the extra burger. One thing to take note of is that this does not necessarily mean that it's the least amount of grams. So this may not be the least amount of grams. And the reason for that is because, again, we have to compare things in moles. And if you need to take the 150 class, you'll cover this in more detail then. What you'll need for 110 is to know the definition. The last part of the chapter is on percent yield. Okay, there's a couple of key terms that are important here. Theoretical yield, which is the maximum or expected amount of product. This is what you actually calculate with math. The actual yield, which is the actual amount of product in a reaction. This is going to be given in a problem. And then percent yield is the ratio of the two. The equation is always the actual amount divided by the theoretical amount, and then because it's a percent, times 100. It should always be less than 100. If it's not, something went wrong. Let's practice the math for this on the next slide. The real-life application of this is pharmaceutical chemistry, and you could be provided with a problem like this. The first thing you need to do when you're solving these is you need to do a mass problem. And after you do the mass, you use the percent yield equation. You'll see here that I have done the mass for you for this example. We were working with Cl2, and then if you keep reading the problem, it says if 10 grams of CHCl3 is produced, so those are the two things we're comparing. We get 59 grams, and then the question asks for percent yield. So we're going to take the actual gram amount of 10 divided by the grams we just got of 59 and multiply that by 100. And we get 16.9%. Please pause the video and try the second problem. Please check your answer. You were given information about NO and NO2, so those are what you're comparing. After your mass, you should have gotten about 76.7 grams, and then you take your actual yield divided by the answer you got, times 100, to get your percent yield. This concludes this chapter.